Hey, my name is Steve. Welcome back to my YouTube channel. This video will cover the last question in 2019 HSC Mathematics Extension 1, question 14. So here's the first question. To prove by mathematical induction for all the integers where n greater than or equal to 1 for these statements. The statement is 1 times 1 factorial time plus 2 times 2 factorial until to plus n times n factorial equal to n plus 1 factorial minus 1. So for mathematical induction, we usually have 3 steps to prove. The first step is usually we are using the smallest number to prove this statement is true. So for here, the smallest number is 1. So to prove this statement for n greater than 1, n equal to 1. The second step is we're assuming when n equal to k, this statement is still true. Okay, so based on the second step assumption, we go to the third step to prove n equal to k plus 1. If this statement is still true, then we can say based on the mathematical induction, this statement is true. Okay, 3 steps. Okay, let's go to the first step. So the first step is when n equal to 1, we have this statement, the left hand side equal to n equal to 1, so we have 1 times 1 factorial. 1 times 1 factorial, so equal to 1, 1, we have 1. Right? And the right hand side equal to 1 plus 1 factorial would be 2 factorial minus 1. So 2 factorial is 2, minus 1, then you got 1. Then, when n equal to 1, the statement is true. Okay, so we have finished the first step. When we go to the second step, we are assuming when n equal to k, this statement is still true. The statement is still true. Such that we have 1 times 1 factorial plus 2 times 2 factorial plus until, so now we are using k, not n, okay? So k times k factorial equal to k plus 1. K plus 1 factorial minus 1. So here's the first step. So here's the second step. Okay? Let's go to the third step. Based on this assumption, we try to prove when n equal to k plus 1. So for when n equal to k plus 1, so this one, the right hand side, we have equal to k plus 1. So this k plus 1 is this n, and then plus 1. Factorial minus 1. So we have k plus 2 factorial minus 1. We have k plus 2 factorial minus 1. So here's the right hand side. So we try to prove the left hand side to have the same result to the right hand side. Then we can say this statement is true by the induction. So we have the left hand side equal to 1 times 1 factorial plus 2 times 2 factorial plus until k times k factorial, and then the last term is k plus 1 times k plus 1 factorial. Okay, here's the last term. Here's the second last term. So from here, the first n term is exactly to this one, right? So we are using this part to replace the first n term, the first k term. So we have k plus 1 factorial minus 1. So this part equals to the first k terms, and plus the last term, and then plus k plus 1 times k plus 1 factorial. Okay, so we have k plus 1 factorial here, and also k plus 1 factorial here. We can combine these two terms and then factor out k plus 1 factorial to have k plus 1 factorial, and then times. So here we still have 1. Here we have k plus 1 combined together, combining these two terms, and we still have minus 1 here, minus 1. So here it would be k plus 1 factorial times k plus 2 minus 1. K plus 1 factorial times k plus 2. Combining these two terms actually is k plus 2 factorial. So we have k plus 2 factorial and then minus 1. This result is exactly equal to the right hand side over here. K plus 2 factorial minus 1. Then this one is equal to the right hand side. Then we can conclude that under the mathematical induction, we can say this statement is true. Okay? So the last sentence is by mathematical induction, the statement is true. So we have 3 steps. So here's the 3 steps for the induction to prove this statement is true. Okay? Great, next one. So here is the second question. Because I have written the answer for this one, because this question is only the explanation. So the question is, the diagram shows the graph of y equal to 1 over x minus k. So here is the graph for y equal to 1 over x minus k. These two curves, where k is a positive real number. So the question is, by considering the graphs of y equal to x squared. So here's one graph, and the other one, y equal to 1 over x minus k. So y equal to 1 over x minus k is this one. Explaining why the function of fx equal to x cubed minus kx squared minus 1 has exactly one real 0. So we can adding this function curve to this diagram to see the relationship between these two curves. So y equal to x squared, the curve would look like this. Crossing the original and cutting with this point. So here y equal to x squared. So we can see that the graph here is the y equal to x squared cutting with the function of y equal to 1 over x minus k at one point only. So there's only one intersection. So that we can say only one intersection point means that the x squared equal to 1 over x minus k has only one real solution. So here is a solution when this curve, this function, equal to this function. There's only one solution here. We can compare this relationship with this one. We can let this function equal to 0. Because here we need an x squared. We can factor out x squared from these two terms to have x squared times, we have still x minus k. So x squared times x minus k, and then minus 1 equal to 0. And then bring the negative 1 to the right hand side to become positive 1. So we have x squared equals to positive 1 divided by this term. So we have 1 divided by x minus k. So this one is exactly this one. Because this one has only one real solution, then we can say this function has only one real zero. But the condition is when x not equal to k, because we can't have a 0 for the denominator. So that we can say this function fx, fx equal to x cubed minus k x squared minus 1 has only one real 0 based on this result. Okay, because this one, so that we can have this one. That's the relationship between the reason and result. Okay. Let's go to the next question. Let's make this 0 to be alpha and let x1 equal to k to be the first approximation to alpha. So the question based on this assumption is, so that we're using one application of Newton's method to give the second approximation to show that x2 equal to k plus 1 over k squared. So from the previous question, we have fx equal to x cubed minus k x squared minus 1. Under the Newton's method, we have the second approximation x2 equal to the x1 minus the function at the first approximation divided by the derivative of the function at x1. So from here, we have to find the derivative of the function of f dash x equal to 3x squared minus 2kx. Okay, so when x1 equal to k, so we are using the k, sub in into here and these two functions. We have k minus, so here this function, so k cubed minus k times k squared, also is k cubed, and then minus 1 divided by 3k squared minus 2k, and here's k, 2k squared, so equal to k minus, so k cubed minus k cubed. So here you can cross out 3k squared minus 2k squared, we still have 1k squared in the bottom, and for the top we still have negative 1, right? So we bring this negative sign into here to become positive, to have k plus 1 over k squared. Okay, that's what we want from the question. So we have x2 equal to k plus 1 over k squared. Okay, this Newton's method is not in the new syllabus. Okay, so this question is not in the 2020 syllabus. Okay, okay, next question. So we have to show that the alpha is in between x1 and x2. So alpha is the only one zero of the function. Here is the function. As long as the coefficient number of the highest power is positive, the curve of the function will roughly look like this, or look like this. So cutting with the x-axis at one point. So this point will be alpha, or this one. So there's only two situations. We can pick this one to explain how to solve this question. Okay, so if the x1 is less than the alpha, if the x1, so here's x1, less than the alpha, so here the fx1 should be less than 0, right? If the x2 is greater than the alpha, it's on the right side. So here x2. if the grade x2 is greater than the alpha, the value of the function at x2 should be positive. So if we can prove the fx1 is less than 0 and fx2 is greater than 0, in that case, we can say the alpha is in between x1 and x2. Okay? So we try to prove this one and this one. So we subbing the x1 into the original function, we have fx1 equal to, because the x1 is equal to k, so we can actually sub in the k into the function for the value of fx1 to become exactly here, would be k cubed minus k cubed minus 1. So here is negative 1. Negative 1. So as I said here, if this one is alpha, then we have proved this one x1. This fx1 is less than 0. So this one is confirmed. So at least we have confirmed this part. The x1 is less than alpha. We try to confirm the other part. The x2, we have found the value of x2 equal to this one, k plus 1 over k squared. We submit this one into the original function just to see whether the fx2 is greater than 0 or less than 0. So fx2 equal to, so here is the x2. So in this one we have k plus 1 over k squared cube minus k plus 1 over k squared and then square and then minus 1. And then you have to explain the bracket, okay, expand it. And then so here is the to the power of 2 to the power of 3. So you remember the Pascal's triangle, we have like 1, 1, 1, 1, 2, 1. So and then 1, 3, 3, 1. Okay. So this one is for the power to the power of 3. So we're using this 1, 3, 3, 1 coefficient to expand this one. So we have 1, so k cubed plus 3, this one square, k squared times 1 over k squared plus 3, so k and then this one square, k plus, so 1 over k squared, we have 1 over k to the power of 4. Okay, so the coefficient is 1, 3, 3 and then 1 plus this number to the power of 3, we have 1 over k over 6, k to the power of 6, and then expand this one, we have minus k and then k squared plus this one times 9 would be 2 over k plus 1 over k to the power of 4 and then minus 1. Okay, and then do your calculation with the k cubed plus, so here's 3 plus 1, we have 3 times 1 over k to the power of 3 plus 1 over k to the power of 6. This times 1 minus k cubed minus 2. This one times this one, 2. Then minus 1 over k to the power of 3. And then minus 1. Good? Yes. And positive 3, negative 2, negative 2. They all cross out. K cubed minus k cubed. Okay, and then 3 times 1 over k to the power cube and minus this one, we still have 2 on k over cube, a to the power of 3, and then plus this one, plus this one. As long as we have k is positive, because k is positive, That's why we have this one is greater than 0. Greater than 0, which means fx2 is greater than 0 over here. So we have a positive fx2. So here it would be x2. Okay? So because fx1 is less than 0, so here's f alpha equal to 0. So this one is less than 0, this one is equal to 0. This one is greater than 0. Okay? So in the curve, so that we can say x1 is less than alpha, alpha is less than x2. Then we can prove this statement, x1 less than alpha and alpha less than x2. Okay? Okay, let's go to part C in the question 14. The question is, the diagram shows the two curves. One curve is y equal to sine x, and the other one is y equal to sine x minus alpha, and then plus k. So this one will be the sine x. The curve on the top is y equal to sine x minus alpha plus k. So the top one is this one. So where alpha is in between 0 and pi, and k is greater than 0. The two curves have one common tangent at x0. So at x0, two curves have the same common tangent over here. And x0 is in the range of 0 to half pi. The first question is, explain why cos x0 equal to cos x0 minus alpha. Okay? So x0 is at this point. At this point. So here's x0. Because these two curves have the same gradient at this point, or same tangent at this point, which means the differentiation of these two functions at x0 should be equal. Okay? Okay, from this result we have, so we can let fx equal to y equal to the first function sine x. Its derivative f dash x equal to cos x. Right? At this specific point x0, we have f dash x0 equal to cos x0. Okay? Okay, another function is we let gx equal to this curve, this function, sine x minus alpha plus k. Okay? And its differentiation g dash equal to cos x minus alpha. And at this specific point x0, we have x0 equal to cos x0 minus alpha. Because these two curves have a common tangent at this point, then we can say since two curves have a common tangent at x0, then we can say then we have cos x0 equal to cos x0 minus alpha. Okay, because these two curves have the common tangent at this point, which means the differentiation of these two functions at x0 are equal. Then we have cos x0 equals to cos x0 minus alpha. Okay, so here's for the first one. Go to the second question. We need to show that sine x0 equals to negative sine x0 minus alpha. From the formula, we have we have sine x0 squared equal to 1 minus cos x0 squared, right? Okay, from previous question, we have sine x0 equal to cos, no. So from previous question, we have cos x0 equal to cos x0 minus alpha. We can use this result to this one. To replace this one, so we have 1 minus cos x0 minus alpha squared, right? And if based on this result, we have, because 1 minus cos f, this angle f squared equal to sine this angle x0 minus alpha squared, right? Which means we have sine x0 squared equal to sine x0 minus alpha squared. Then we have sine x0 equal to positive or negative. We take off the square. It's negative and positive sine x0 minus alpha, right? And because at these two functions, at this point they have the same value of this. So we have sine x0 at this point equal to the sine x0 minus alpha plus k. We can use this result into here. So because we have sine x0 equal to sine x0 minus alpha plus k. Since k is not a zero number, positive number, which means we cannot choose, so sine x0 cannot be equal to sine x0 minus alpha, which means we cannot choose a positive result for the sine x0, which means sine x0 has only one result, but it's a negative. It's negative sine x0 minus alpha. Okay, so because this k is not a zero, if k is 0, then we have two answers. So we can have sine x0 equal to sine x0 minus alpha, but k is positive, then we can't have the positive number here, which means the only one result is negative. So sine x0 equal to negative sine x0 minus alpha. So here match the result, match the question. Okay, last one. Hence or otherwise, to find the k in terms of alpha. From this relationship of the alpha and k, we can find the equation for k in terms of alpha. So because sine x0 equal to sine x0 minus alpha plus k, right? Because sine x0 equals to negative sine x0 minus alpha, then we can replace this one with this one. So we have negative sine x0 minus alpha equal to sine x0 minus alpha plus k. Usually this kind of question, within a big question, you have to think how to use the result from the previous part. For example, in the third part, we use the result from, we may use the result from the second part and the first part. So in the question, in the second part, we try to think about how to use the result of the first part. Okay, so here we are using the result of the second part for here. So we can combine these two. So bringing this one into the other side, we have so negative 2 sine x alpha x0 minus alpha equal to k. So here is the function for k in terms of alpha, but we have a x0 over here. x0 is not a specific number we know, and x0 is not a variable in the function for k. So we are looking for the function for k just in terms of alpha. We should have one variable for this function. So we try to deal with this x0. So we are using the result from the second part of sine x 0 equals to negative sine x 0 minus alpha. So we have sine x 0 equal to, so because sine x 0 equal to negative sine x 0 minus alpha. Because sine is the odd function, which means negative sine angle equal to sine and negative angle. So x0 minus alpha. This is because sine is an odd function, okay? Which means x0 equals to this part. So we have x0 equal to negative x0, negative x0, and then here is positive, plus alpha. Here is a function of alpha and x0. We can replace the function, we can replace the x0 with something of alpha. So we can bring this one to the other side. We have 2x0 equals to alpha, which means x0 equal to alpha on 2. Then we can replace the x0 with half alpha into this function. We have k equal to negative 2 sine. So x0 using this one will be alpha over 2 and then minus alpha. Become negative 2 sine. So here will be negative half alpha. And also because sine function is an odd function, we can bring this negative sign outside the sine function. We become, so negative to become positive. So at the end we have 2 sine alpha on 2. Eventually we are getting a function for k in terms of alpha only. So only one variable in the function for k. Okay, that's the result. Okay, that will be all for the 2019 HSC Mathematics Extension 1 past paper. In the next video, I will starting from the 2018 HSC Mathematics Extension 1 past paper. Hopefully my videos will help you to have a much better preparation for your HSC exam. I'll see you in next video. Bye bye.